Hi everybody, in this video we are going to go over how to transform graphs, particularly the cubic equation or x to the third power. So let's get into it. This graph over here, x to the third power, y equals x cubed, is the parent function of all cubic equations. If we wanted to look at it from the standpoint of a, h, and k, I'm going to kind of ignore b for now. X minus 0 cubed plus 0. That all means what, you may ask? The rules are as follows. So here A is going to cause either vertical reflection, stretch, or compression. It wouldn't matter if we did have a B value, in the sense that it can cause a horizontal reflection, which is more or less exactly the same thing as a vertical reflection. The changes do occur that B is a compression or stretch, and they work out in different ways, and in future videos it will elaborate on that. But for right now, for what we're going over, it's more of a regular level algebra 2 pre-calculus standpoint. We're just going to focus on A, H, and K. H, when there's a 1 in front in this format, shifts right when it's a minus and shifts left if you have plus H. And then up and down, the K is pretty normal. I've elaborated on this in previous videos: linear, absolute value, and quadratic. So all that's there. So let's dive into this example. So this moves right 0, up 0, and it has this standard shape because of the 1. So 0 to the third power is 0. That's really where that point comes from. 1 to the third power, which is 1 times 1 times 1, is, you guessed it, 1. And then 2 to the third power, 2 times 2 times 2, no, it's not 6. It's 8. So we got 1 and we got 8. The next one would be 3 to the third power. That's 27. It's up pretty high. Then we go 64, 125. It's just, we're not fitting that. Then when you cube negatives, they're different than when you square negatives. When you square something, second power or any even power, you're going to get a positive output. But when you raise negative numbers to odd powers, you're going to get a negative output. So we're going to look over here more in quadrant 3 instead of quadrant 2. Negative 1 times negative 1 times negative 1 is negative 1, and negative 2 times negative 2 times negative 2 is negative 8. So we're here. Now, just as a shortcut, it's not a good trick because you can't do it like with quadratic, so we could go up the odds 1, 3, 5, 7. Here, not so much. We can go up 1. We can go from that 1 up 7, just so you don't have to count all the way, back down. You save yourself a microsecond. Over 1 down 1, over 1 down 7. Okay? I'll elaborate on fancier videos, but for now, good. Positive cubic polynomial, so it's positive leading term. That means the right side is pointing up for end behavior. Odd means the beginning, the left side is the opposite, so that is down. So you would say the end behavior is down and up. The domain, it goes left forever, although it is going down much faster than it is going left. It is going to continue to go left. I can plug in -3, -4, -5, and continue to get outputs. So the domain starts with a parenthesis, not included, from negative infinity, and goes to the right, forever the same way, to positive infinity. And the range, similar to a linear equation, which is also odd powered, the range is also negative infinity until infinity. So all real numbers are used up over here. And also similar to a linear equation, the symmetry is called odd. As I indicated on the first video, that would mean the f of x is equal to the negative f of negative x, or whatever rearranged ways I wrote it down over there. And that's it. That's it. Over 1 up 1, over 1 up 7. Make yourself some notes, write it down, remember it. That's what it looks like. Next, here I'm in the horizontal house, so that right there moves us to the right 4, and that moves us down 6. Nothing else has changed. Right 4, down 2, 4, 6. Nothing else has changed. The shape of the defaulted standard cubic graph, that guy right there, is the shape. This is where you plant your seed of your cubic, and it's bloop, gonna grow from there. Over 1 up 1, over 1 up 2, 4, 6, 7, over 1 down 1, over 1 down 2, 4, 5, 6, 7. I'm off. I'm right over there. I don't know if you could see it. Some vocab for us, actually. I wouldn't call this point a vertex. I would call this one a point of inflection. A point of inflection is a point where your concavity switches from either concave down to concave up, or reversed, concave up to concave down. This part here is concave down. If you look at how it's curved, concave down looks like a frown. Concave up looks like a cup. doesn't look like, can't say happy face, doesn't rhyme, but that's concave up, that's concave down, so that would make that spot a point of inflection. It's not a vertex where it's like the extreme high or low point of a graph, it's a point of inflection, okay? This graph is increasing on its entire domain, just to show, use some other vocabulary. Next. Let's just, there we go. Okay, so this over here I could also rewrite just to look at a little bit more in HK form. Okay, now how do you know it's a cubic function? It's cubed. It's that third power. The house the graph is enclosed in tells you what kind of graph it is. So where is this moving? Well, it's moving right, nothing, up, 2. And that negative over there, what does that do? Vertical reflection. So it's going to flip up, down because of the negative in front. Okay? So 3 different transformations written out. So where am I going? So right 0, up 2. That is my newly calibrated origin point. That's where I'm planting my cubic graph seed. Early, when you first start graphing these things in an early algebra 2 or pre-calc class, you're probably not going to see a lot of stretches on this. Maybe a compression of a half or something. In that case, over 1 up a half instead of 1, over 1 up 3.5 instead of 7. Half of your usual. But you're probably not going to see a stretch because you're going to be going up 2, 14, you're up 16 points. It's kind of large. The negative goes over 1, down 1, over 1, down 2, 4, 6, 7. Then over 1, up 1, over 1, up 2, 4, 6, 7. So graph concave up, watch your curve. Concave up, and then concave down. There we go. That's our nice little point of inflection. The end. The next one, where are we going? We are going left 3, down 1. Got it? Left 3, down 1. Left 3, down 1. And again, it's negative. Again, these are light examples. Don't get used to it. It's not going to be like this forever. It is another vertical reflection. So it's going to look like this. Over 1, down 1. Over 1, down 2, 4, 6, 7. Over 1, up 1. Over 1, up 3, 4, 5, 6, 7. Again, nice and easy. Concave up looks like a cut. Concave down looks like a frown. There you go. Where is that point? Your point of inflection is at -3, -1. This graph is, both of them are decreasing on their entire domain. And there you go. So we are, 823. Nice. If you kind of get it now, this is how we graph this. So a cubic looks like a parabola with a broken arm. So it's like a parabola, bloop, one arm fell down. So make that nice scoop shape. This is probably one of the ugliest graphs people draw. I don't know what the heck the problem is. I don't think you're trying very hard, to be honest, but whatever. Thumbs up if you think you can graph a transformed cubic function. If you have a question or a type of example or some issue about how to graph something, if it's not in this form, that's going to fall under the umbrella of graphing polynomials. So look for that video. I have tons already done, and I will be doing more. And comments in the comment section. Answer somebody else's question if you can. Thumbs up if you feel a little bit smarter. Adios. Look for the next one, which will be square root graphs.